So what is a Hamiltonian cycle? If we are given with a graph with set of vertices represented as V and set of edges represented as E, and we consider it to be a connected graph with n number of vertices in it, then a Hamiltonian cycle is a round trip path along n edges of G that visit every vertex exactly once and it returns to its starting point. That is, in a given graph, you are going to start from one vertex called the source and visit all other vertices exactly once, such that you are not going to visit these vertices again and get back to the starting vertex. That is what we called it to be the source. So in this particular graph, in the first example, we can obtain Hamiltonian cycles as or by visiting vertex 1 to 2 and then 2 to 8 and then 8 to 7, then 7 to 6, 6 to 5, 5 to 4, from 4 to 3 and then from 3 to 1. So here if you observe, we have been traversing every vertex exactly once. This is one example of an Hamiltonian cycle for this given graph. There can still exist many more Hamiltonian cycles for the given graph. So we can also consider one more example there. So now let us look into the algorithm to find Hamiltonian cycle. So we have two bits to this algorithm. The first one is Hamiltonian of k and the next bit is the other algorithm to find the next value. So this Hamiltonian of k is a recursive formulation of backtracking to find all Hamiltonian cycles of the graph. The input to this algorithm is the adjacency matrix of the graph. So we'll have to first fill in or form the adjacency matrix. This problem is started by first initializing the adjacency matrix and then setting the solution vector x from the solution vector x from the position 2 to n to zeros, and x of 1 is always set to 1, and then we start executing Hamiltonian of 2. So we always set x of 1 is equal to 1 because we want to get distinctive cycles. So we fix the source to be vertex 1. So now this algorithm runs for infinite number of times, right? That is unless a solution has been obtained. So initially we assign x of 2 to x of n to zeros, and then we make a call in this repeat loop. We make a call to function next value of k. So this next value of k is called in order to assign a legal next value to x of k, that is to find out the next available vertex that can be included into the Hamiltonian cycle. And in case if we are not able to find out the next vertex, then we will have to backtrack to its previous vertex, which is done by this statement: if x of k is equal to 0, then return. Right? So for example, if I am computing Hamiltonian of 3, right, and then I find that I have no other vertex to reach after vertex 3, then h of 3 will yield me a value 0, wherein I'll have to backtrack to a function call that is Hamiltonian of 2. Right? So please remember this statement: if x of k is equal to 0, then return is going to perform backtracking. And then in case if we have found out the next vertex, that is x of k, which is not equal to 0, then what we do is we need not have to perform backtracking. So we try to check if this next vertex k that we have found out is not the last vertex in the graph by making use of the condition if k is equal to n. So in case if the vertex that we have found out is the last vertex in the graph, then it means that we have already found a Hamiltonian cycle. So therefore we simply print the contents of our solution vector. Otherwise out, if we have not found, or if the vertex that we have found is not the last vertex, then we make a call to function Hamiltonian, but this time the argument would be k plus 1. That is the next vertex that is to be found out. Okay, so the next piece of algorithm here is next value. Okay, so what does this next value algorithm do? So it's going to find out a path of k minus 1 distinct vertices. If x of k is equal to 0, then no vertex has yet been assigned to x of k. After execution, x of k is assigned the next highest numbered vertex, which is not already appearing in the solution vector and is having an edge back to its previous vertex given by the column in the solution vector x of k minus 1. X of k minus 1. Otherwise, if x of k is equal to 0, that is, if you don't have a suitable vertex that can be visited, then the column would be set to 0. And if k becomes equal to n, it means that it is the last vertex in the graph. Then you need an additional edge from x of k, which is connected to x of 1, because it's a cycle. So repeat until similar to that of our do while loop. So in this do while loop, the very first statement is initializing the values of the solution vector. So let us say we had made a call to Hamiltonian of 2. So here is our example graph. Let us say that this is our solution vector, which has first column, second column, third, fourth and fifth column. So as we have only 5 vertices in this given graph, so initially x of 1 we have already assumed it to be the source vertex, that is, we always consider source vertex as 1, so we fix it to 1. And then Hamiltonian of 2, so the case value was 2, so coming here x of 2 we are trying to find out. So x of 2 to x of n is initially set to 0. So x of k is 0, 0 plus 1 is 1, 1 mod n is 5, 5 plus 1 is 6. So it gives me a value okay. So we start from x of 2, which is equal to, as I had already told you, so x of 1 will be initialized to 1, x of 2 will be set to 2. So x of 2 is equal to x of 2, that is 0 plus 1 is 1. So 1 mod n plus 1, n number of vertices, n is equal to 5, 5 plus 1 is 6. So 1 mod 6, I'll get a value as 1 itself. So x of 2 was previously 0, now it becomes 1. And then I check to see if I have obtained the next vertex or not. So if x of k is equal to 0, then we say that there is no vertex and it returns back to the function called Hamiltonian algorithm, right? So now if x of k is equal to 0, x of 2 is equal to 1, which is not equal to 0, so we come to the next line. So here we try to find out if there is an edge between x of k minus 1 and x of k. So x of k minus 1 is vertex 1 and x of k is also vertex 1. So we do not have an edge from vertex 1 to vertex 1 itself. So therefore this statement becomes false. So we do not have an edge from 1 to 1. So the value becomes equal to 0. So therefore we get back to x of k. So this time x of 2 is equal to x of 2's current value is 1. So 1 plus 1 becomes 2. So 2 mod 5 plus 1 is 6. 2 mod 6 is 2. So the new value of x of 2 is now equal to 2. So now again, if x of k, that is x of 2, whose value is 2, is not equal to 0, so therefore this statement will not be executed, and we come to the next statement wherein we try to find out if there exists an edge from x of k minus 1 is vertex 1 to vertex 2 in the graph. So we have an edge from vertex 1 to vertex 2 in the graph. Then it says that there is an edge. So what we do is we enter into the body of the if statement, and here we check for the distinctiveness of the vertex. That is, we have already seen the constraints for the solution vector, wherein we say that every vertex must be visited exactly once, therefore they should be distinct. The vertices should be distinct. If same, then again we are going to break out. So here for j is equal to 1 to k minus 1, k is initially 2, so 2 minus 1 is also 1. So we are going to check to see that x of j, j's value is 1, x of j has an element 1 in it, which is equal to x of k. K's value is how much? 2. So x of 2 has a value 2 in it. So 1 equal to 2 is false. So therefore the vertices are distinct. So we do not execute this break statement. We come to the next line here. So if j, yes, before we come to this line again, then there will be an j plus plus. So j was previously 1, now j becomes equal to 2. So here after it, coming out of the for loop, when j is 2, then 2 is not less than 2 minus 1, so we come out of this for loop. If j's value has now become 2 and k's value was also 2, if j is equal to, that is k, that is 2 is equal to 2, then it means that the vertices were distinct. So in that case, you check the next set of conditions, that is if the vertex k is less than the last vertex, right? That is if vertex k is how much? Vertex, it is 2. 2 is less than, total number of vertices are 5, right? So 2 is less than 5, so it is not the last vertex. Therefore, we again move on to finding the next vertex. Or the condition could be, if this condition is false, that is 2 is less than n is false, and let's say k is equal to n, that is the vertex that we have found tends to be the last vertex in the graph, then we also check to see that in the adjacency matrix, do we have an edge from x of n, that is the last vertex, to x of 1, that is the first vertex in the solution vector, right? So if k is equal to n and g of x of n, there exists an edge from x of n to x of 1, it means that we have got an Hamiltonian cycle, and we simply print the result and come out of it. So printing result is done in the algorithm Hamiltonian. So once we are done with this next value algorithm, the control is going to jump back to Hamiltonian algorithm to a line wherein we are going to check to see if k is equal to n. So if this, when this condition becomes true, there we have a for loop in which we are simply going to write the list of vertices that we have already visited. So we have created a class called as Hamiltonian Cycle, in which we have created a two-dimensional array A with a capacity to hold 100 elements in it, and then we have declared a single dimensional array X with a capacity to hold 10 numbers in it, and n stands for the total number of vertices in the graph. And then this is the constructor. The name of the constructor would be same as that of the name of the class. So the constructor name is Hamiltonian Cycle, in which we have created an object called as source, which is of the type class scanner, by using the dynamic operator, memory allocation operator new. So after it, we are asking the user to enter the number of vertices of the graph. So n is read with the help of a scanner object by invoking the method nextInt, as n is an integer number. And then, as we have already seen in the theory, just in order not to repeat the same cycles again and again, we set the starting vertex to be 1. So therefore, in the solution vector, the very first value of the solution vector, that is x of 1, is set to 1. And then rest of the values of the solution vectors, that is ranging from 2 to n, shall be set to 0. And then we ask the user to enter the adjacency matrix. So we already know that a graph can be represented with the help of an adjacency matrix. Here we ask the user to enter the adjacency matrix. So we already know that the graphs can be represented with the help of adjacency matrix. So this two-dimensional array is read with the help of two for loops wherein I ranges from 1 to n and j ranges from 1 to n. So each element of this two-dimensional array A is read with the help of the scanner object by making a call to function nextInt. And then the next function that we have here is next vertex, to which we pass the current vertex k as the input argument. So initially j is set to 1, and in this while loop, very first thing that we are going to do is we are going to find the values of xk. So xk is nothing but the next vertex that is to be visited in the Hamiltonian cycle. So it is obtained by x of k plus 1 mod n plus 1. So we have already seen why do we make use of this n plus 1. So if xk is equal to 0 means that there is no vertex that is identified. Therefore, it returns back to Hamiltonian algorithm. So in the graph, after the vertex k, if you are not able to find the next vertex, then xk would be set to 0. Then if the condition is true, you are going to return back to function Hamiltonian. Therefore, basically these two statements are used for backtracking purpose. And in case if this condition is false, we come to this statement: if a of x of k minus 1 comma x of k is equal to 1. That means that there are two vertices identified in the solution vector. One is at the location k minus 1 and the other one is at the location x of k, in the location k. So we try to find out if we have an edge from xk to xk minus 1, right? So if there is a edge, then this value will not be equal to 0. So basically the adjacency matrix is a Boolean matrix. If there exists a edge from k to k minus 1, then we'll be representing it as 1. Otherwise, if there is no edge, then we'll be representing it as 0. So therefore, if there is a edge, then we enter a for loop where we try to check whether all the vertices that are listed in our solution vector are distinct or no. So starting from vertex 1 to vertex k that is being identified, you try to check if x of j is equal to x of k. If they are same, then you break out. Otherwise, if they are distinct, then you come and find if j is equal to k. That is, if every vertex is visited exactly once, then the vertices are distinct. So in that case, if this condition is true, then you check to see if k is less than the total number of vertices in the graph. If this is the case, then again you go back to while statement. Again you start with the execution of the statement xk is equal to xk plus 1 mod n plus 1. Otherwise, if this condition is false and this condition tends to be true, that is, if k is equal to the last vertex in the graph and there exists an edge from the last vertex to the first vertex in the graph, therefore we read it as x of a of x of n comma 1. If it is equal to 1, it means that there is an edge from last vertex to the first vertex in the graph. It means that you have found the Hamiltonian cycle. So therefore you make a call to statement return. So when this statement return is called, you are jumping to this line in get h cycle. So get h cycle is nothing but similar to that of our algorithm Hamiltonian. So if k is equal to n, then you are simply going to print the contents of the solution matrix in the order that you have obtained the values in it. So starting from 1 to n, you are going to display the contents of the solution matrix X. that is every value in x of I. And in case, I've already told, if the matrices were not distinct, if you did not get the next vertex, then again you have a return statement. You jump here to this line, the control jumps here to this line, that is if x of k is equal to 0, then return. So for example, if I had made a call to Hamiltonian of 3 and then I was not able to find the next vertex that has to be visited, then this next vertex algorithm would send the control back to this line, wherein this line would make a return call which would again call Hamiltonian of 2. That is, from Hamiltonian of 3 you are going back to its parent, that is Hamiltonian of 2. So you are backtracking. Okay. So in case if this k was not equal to n, then you jump to the else part of it, wherein you again make a recursive call to get Hamiltonian cycle of the next vertex, that is k plus 1, and the function continues until the path is found. So how are we going to make a call to this function next vertex, or it will be the get h cycle function is done in a class called as Hamiltonian cycle expression. So in this Hamiltonian cycle expression we have the main function. So in main function we have created an object called as obj, which is of the type Hamiltonian cycle. So Hamiltonian cycle is a class which has a constructor. So this constructor is going to initialize the contents of our source vector x. It's also going to read the contents of the adjacency matrix, and then the next vertex algorithm which tries to find the next vertex to be visited in the Hamiltonian cycle. And this get h cycle function is going to check to see that if the Hamiltonian cycle is found, then print its result. If not, again make a call to find the next vertex in the Hamiltonian cycle. Right? So then using this object, that is obj, we make a call to function get cycle, but this time we are going to call it with a value, or call it on the vertex 2, because we have assumed that our Hamiltonian cycle always starts with vertex 1. Therefore in the solution vertex we had already set x of 1 is equal to 1. So therefore we started from vertex 2. For better understanding of this practical, you should also refer to a lecture, a theory lecture on Hamiltonian cycles. Let us give this graph as an input to this program. You can see that I have written an adjacency matrix for the given graph. If there exists an edge from vertex 1 to vertex 2, then I represent it as 1 in the graph, and if there does not exist an edge between two vertices, then I simply put a 0. And I have also written the solutions that we are supposed to obtain. So Hamiltonian cycle, as we have set source vertex to be 1, then I'll have to visit all other vertices exactly once. So I'll be having two possible solutions. To start from vertex 1, go to 2, go to 3, 3 to 4, and back from 4 to 1. So similarly, the other possibility could be start from 1, go to 4, from 4 to 3, 3 to 2, and back to 1. Right? So let us see if our program is doing the same or no. So let me run this. So it is asking to enter the number of vertices, the number of nodes. So 4 nodes. Let me enter the adjacency matrix. Zero, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. So look at the solution. So we have obtained 2 Hamiltonian cycles here. So the first solution is from vertex 1 to 2, 2 to 3, 3 to 4, 4 to 1. And the other solution is from vertex 1 to 4, 4 to 3, 3 to 2 and back to 1. Let us give the second input to the program, the second graph. So if you see, it has 2 pendant vertices, 5 and 6. So from 5 and 6 we do not have an edge to get back to the starting vertex 1. So therefore for this given graph we cannot have a Hamiltonian cycle. So besides it, I have written the adjacency matrix for the given for the given graph. So now let us feed this input and check what would be the possible result. So let me run the program again. This time we have 6 vertices in the graph. So the adjacency matrix is 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, followed by 0, 0, 0, 1, 0, 0. So now I am done with entering the adjacency matrix. Let us see what would be the output there. So if you can notice, it is not giving us the Hamiltonian cycle. Thank you.